Well, thank you for the invitation to come and speak. I will try and be tidied up by about 10 to. I'm Dominic Kelly. I'm a paediatrician. I spend a good part of my life in the Children's Hospital in Oxford, wherever the pointer is there. Nice view at night. And the rest, when I'm not at home, at the Oxford Vaccine Group, amongst a large team of vaccine researchers. I've been asked to come, I presume today, with some experience about vaccines and some of the ethical issues around that. I've probably had as little as it's possible to do being part of the vaccine group in the development of COVID vaccines for many reasons, but the group I work amongst were the people developing the AstroZeneca COVID vaccine. My remit today, I was told to develop your scientific and ethical literacy regarding vaccinations to help navigate polarised and competing claims. And I've reordered the list of things I was going to talk about. Really, I'm hoping to give you a scientific literacy around vaccines, the sort of thing vaccinologists think about when they're developing vaccines. I'm hoping to point to some of the ethical issues raised by the work we do, and I've mixed it in with a little bit of actual data about COVID vaccines and other vaccines, so I hope that's acceptable. And I'm very happy to have questions and discussions as we go along. We can stop at 10 to, even if we haven't got to the end. So if things occur to you or you want to talk about them, very happy to do that. The context, which has run off the edge of the screen, which doesn't look a good start for this, but anyway, three major things to remember about vaccines. They're essentially, a good Catholic concept, a natural method of protection. I mean, there's almost no other medicinal project that works as straightforwardly. You give something that looks like the pathogen, either the whole thing or a bit of a structure of a bit of it, to trigger the immune system, to give you immunity without causing illness. There's our green virus, the live virus. We either weaken it, and it looks the same, and the immune system thinks about it as a virus, or we kill it, we take the heart out of it, and it still looks like the shape of a virus, or we're very clever and we can work out which bits of it are actually important for inducing immunity, and we just give you those rather than the whole thing. So it is a very, we're making use of the normal process of immune response to protect from infection. The second thing is the absence of major infections from childhood. Vaccines work for the most part, or there are many vaccines which are very effective. Our life, family life, particularly hospital life, is profoundly affected by the absence of tetanus, diphtheria, whooping cough. I mean, the list goes on, a long list. That also is a problem for vaccines because the diseases we're preventing aren't seen very much, and people's perception of the risk is actually not very realistic. And the third major theme is that in order to deliver routine immunisations, we're doing it, we're administering at large scale to completely healthy individuals, often perceived as quite vulnerable, infants in the routine schedule, for diseases people don't see. And so the tolerance for adverse events is very, very low. These have to be very safe. And the scale requires significant institutional involvement. So we're in a setting where the idea that we're in a setting that is almost set up to breed controversy if you have suspicions of state involvement in anything, and because we do see adverse events. I'm going to run through a list of the things vaccine people think about when they're considering any vaccine problem, and particularly this is in the order in which one might take things in terms of design when you're designing a vaccine. The first thing you have to know about is disease epidemiology. Is this an important disease? Is it affecting people in a severe way? Is it worth bothering any time to develop a vaccine? Most of the time we're faced with stable illness, stable patterns of illness, stable patterns of disease, things that have been around a long time, we understand quite well. In the pandemic, we're faced with a completely new disease. The question about burden, is this worth doing, was really, I say a no-brainer, I don't really like that phrase, but it comes to mind when you see pictures of Wuhan with health systems overwhelmed. If this is going to spread, this is going to be a significant problem. I think the thing we always underestimate is our lack of knowledge, and Gavin is very good at reminding us of that. I think people assumed when they saw Wuhan that this would be like the original SARS 20 years ago, which was severe, and most people who got it got sick. We're a little bit relieved when that turns out not to be the case, but it actually turned out to be worse than that. If you've got enough people who get sick to cause you a problem in a health system, but many people not getting sick but transmitting it, then you can have a lot of transmission and things that are out of control before you realise it. And that's essentially what happened with SARS-CoV-2, with COVID. with the original disease, enough people were sick, you identify the case, you isolate them, you wait for the next cases, you isolate them, and you can control things. But this had spread very widely before people really were on top of it. You'd also like to know about the age-specific burden. And this is just some data from the Department of Health, and it is by age, the number of deaths, people who died within 28 days of a positive test for COVID. We could argue about the definitions, but essentially some measure of the severity of COVID. And it shows you that if you look at the rate per 100,000, not just the total numbers, that young people were very unlikely to die of COVID, and the older people you got, you were much more likely to die of it, and that's quite well established. This was a disease where early on we knew children weren't affected, which is my area of interest. Another nod to how little we know is that completely unexpectedly in April of 2020, we began to see children with a very marked inflammatory condition, which we'd seen similar things before. We had an idea what sort of thing it was, but it very quickly became clear this was going to dominate paediatric life for about 2 years, and it did. So we'd not predicted that COVID would do this. Probably 1 in 5 to 10,000 children who got it ended up in hospital with an inflammatory syndrome. About half of were in intensive care. And that was dominant for 2 years, and then just as quickly as it had come, it went. And we haven't seen almost any since January of last year. So just interesting times. From an ethical point of view, I'm still astonished, or continue to be astonished, by the slow burn of fallout from COVID for children and young people in terms of the mental health issues on the wards and the behavioural issues in schools. And I haven't really been bought into this, but it just seems to be a slow burn that keeps on coming up. And, you know, as a result of lockdown, missing education, presumably, and certainly for 2 of my adolescents, I was impressed at COVID as being a crisis that didn't need anything of them. It put them to one side, they couldn't get on with what they were doing, and yet the actual risk to them of disease was tiny. And actually that's what we've seen, really. The risk to the children in the hospital, we see very, very little severe disease. A couple of exceptions: children with Down syndrome, almost the highest risk for severe COVID, even more than age and obesity. Downs has something funny about it, and neurodisability. But COVID really, really has avoided children in a most exceptional way, I think, and we still don't really understand that. So we want to know something about the age-specific profile. If we're talking about ethics, there are a lot of interesting things around transmission of infection versus disease. Is your vaccine to prevent people getting sick, or is it to prevent people getting transmission? Ideally, you'd like it to do both. But what if you can prevent transmission by giving it to a group who don't get sick? Are you going to immunise children, for instance, to prevent adults getting sick? And we'll come back to that in terms of herd immunity, but quite a lot of ethical interest around that. And the other thing about disease epidemiology is just strain variation. Vaccines are developed by people with the money to develop them. It's usually quite a lot of money. People focus on strains in countries where there are money, where there's funding to do it. And for a large part, that's America, that's Europe. And so there are several examples of vaccines that have got very high need in Africa, in Asia, but have been specifically developed in the first instance for strains prevalent in the resource-rich countries. So if we're thinking about ethical issues around vaccination, I think that's one of them. Types of vaccines, I always think of this as leading into the issues that as Catholics we're quite interested in. But here's a sort of almost a history of vaccine biology. These are different types of vaccines, starting from the sort of 18th century live organisms that are a bit weakened, that have been attenuated, through to organisms that are killed, through to us identifying in the early 20th century or late 19th century the actual toxins produced by the bacteria that like tetanus and diphtheria that we could use as vaccines, and then getting progressively more sophisticated about picking out individual proteins and just giving those proteins from the bugs. And then different ways of presenting those proteins on little blebs called vesicles or in virus-like particles. And then molecular biology allowing us to conjugate bits of the protein to other aspects of the organism, through to the more modern DNA and RNA vaccines, but essentially getting progressively more refined versions as we understand how to produce immunity just to single targets within the bug. In a way, it's surprising that the technologies that produced the first vaccines for COVID were from the sort of more modern end of the spectrum. The Pfizer and the Moderna vaccines were these little what are they, little encapsulated strands of genetic material that you gave. The genetic materials coded into proteins, and you essentially get a vaccine that way. The AstroZeneca vaccine was a virus that you then put in the gene, a harmless virus that you put in a gene for the COVID protein. The reason those were the first and most successful was in part there had been significant investment in pandemic vaccines, actually, certainly in Oxford in the 3 or 4 years before, around another coronavirus. So this was almost ready to go. But in part because these modern vaccines allow you're very easy to synthesize a bit of genetic code once you know the gene for the virus, pop it in the same platform or particle, and then away you go. It's very easy to change the thing you're vaccinating against. Whereas for all the others, you actually need to synthesize, make the virus, you need to specifically, and if you've never met it before, you need to learn how to grow it, or to work out which bits of the protein, how to make it fold properly, how to manufacture it. So the COVID vaccines that were successful were the most modern technologies, and in part because they're designed to be ready to go very quickly. In terms of the ethics around types of vaccines, we talked about the diseases people choose to focus on the strains. They're normally not the ones with the highest burden of diseases in the poor areas of the world. And I guess that's equity of access. They're also not usually made to be especially cheap. And the capacity to deliver enough to vaccinate a lot of the world means that vaccines are sucked up by the richer countries. And there's some interesting exceptions to that in terms of people now with the malaria vaccine that's in Oxford now choosing to have that made in India, where they've got massive capacity at low cost, so they can then provide vaccines that are affordable, and people transferring technology from Western companies to companies, again, able to manufacture at scale to produce vaccines, niche vaccines for Africa. And there's been epidemic meningitis from meningococcus that's had that process very successfully undertaken. Integrity of process I put there because I'm always worried Gavin's going to ask me about human embryonic kidney cells and growing viruses. There are live viruses, the adenovirus vector here for the AstroZeneca vaccine, and other live virus vaccines have to be grown in cells. There's a well-understood cell line, HEK293, derived from an aborted fetus in the 1970s, that gets people very exorcised about whether I can't remember what the word is it cooperating with evil? Is that the technical term? I lose my way a bit. I'm interested to talk about that. I have a pretty clear view on it, and I think it's probably difficult to engage in molecular biology without somewhere down the line your reagents having come from one of these cells. I don't think it's the most important ethical issue in vaccine biology, but we can talk about that at the end. I'm not going to talk about route of administration too much, but essentially most vaccines are given by injection into the muscle or under the skin. Occasionally we squirt them up the nose. People are considering different ways of giving vaccines, but it's an important area for vaccinology, but perhaps not one for us here today. Adjuvants. So Janeway was an American immunologist, died about 10 or 15 years ago, and who discovered some particular important receptors, pathogen recognition receptors in the immune system. But he said that immunologists' dirty secret was that if you just give a protein, even a foreign protein to a human, they don't develop a good immune response. Just a protein on its own, the body doesn't get that excited about. You have to give it and convince the body this is a threat to them. You can do that by giving the protein with the whole bug, and the body's very good at recognizing that bugs are bad for them, or you can convince the body that something bad is happening by giving something called an adjuvant. The adjuvants we use are, a variety of things, but until recently there was only aluminium salts. So we give salts of aluminium, you absorb the protein onto it and you give it in that. And increasingly there are slightly more sophisticated molecules with funny technical terms that companies have patents on, but essentially soup up the immune response. They're very important. If you want to make your vaccine cheaply, you want to give as little of the vaccine antigen, the actual vaccine itself. If you give a cheap adjuvant with it, you can use less antigen and make more doses. So if you only have to give 1/10 the dose of your malaria vaccine, you can make 10 times as much. People get exercised because these stimulate the immune system and because they worry about toxicities in terms of aluminium being given, and so aluminium or some of the other chemicals. And quite right, very reasonable to raise those questions. And I think information is a big ethical issue for vaccinologists, providing good quality, reliable information. And I would point you, if you're interested in these issues, to the vaccine knowledge part of the Oxford Vaccine Group website. A lot of time and effort has gone into trying to provide reliable, good quality, referenced information on how vaccines work and components. And also the Department of Health produces a very good publication called The Green Book, which is available online and has succinct but comprehensive information on all kinds of aspects of vaccines if you're ever asked about them. Clinical trials. So we're not going to talk about preclinical development in animal models, but once you've got a vaccine that you want to take into humans, you assess it through a variety of clinical trials. And this is where statistics become very important, and doing a well-designed trial with a statistically sound outcome. And we divide them into phase 1, 2, 3, and 4. Phase 1 studies are essentially first in human, the first time you've given this vaccine to anyone, trialling it for safety. Does it make you very sick? Does it give you a very sore arm? Is there something unexpected about it? And they tend to be tens of patients. And phase 2 studies are usually a larger number and measuring mainly about safety, but also about immune response. So the two important areas of vaccines that we assess in phase 1 and 2 studies are, do they give you any nasty reactions, sore arms, fevers, fits, something more dramatic, and do they give an immune response? And that's the reactogenicity and immunogenicity. I'll mention immunology very briefly. Immunology is an extraordinarily complicated area, and being a complicated biomedical science area, it's full of poor data and publications. And I mention it just because you will read all kinds of articles quoting this aspect of immune response or that aspect means X or Y or Z. It's very easy to find some interesting things to talk about. But essentially, when we're measuring immune response in vaccines, the only things we really understand well are antibodies. The proteins in the blood that generated by the vaccine that grab onto the bug. And essentially most vaccines are developed based on what sort of antibody response they give. We measure how much antibody, we measure a bit about how well it works, but that really is our primary outcome. We're interested in the cells, the T cells underlying these things. There are all kinds of other cells, but understand them very poorly. So essentially most studies that you see presented will measure antibodies. Reactogenicity is an important issue for public use of vaccines because it's what people see first when they give a vaccine. Sore arms, fevers, convulsions. Vaccines can give all these things, and there's something we assess in those early phase studies. If you do 100, 200, 300 people in a phase 2 study, you will have a good idea how much reactogenicity it gives. And this is a study where someone's having the area of redness or swelling measured on their arm. We talk about local reactogenicity, which is sore arms. We talk about systemic, which is fatigue, taking yourself to bed, headaches, things that aren't local to the actual injection. These are important areas to understand well because they are important areas of public scrutiny. Some interesting, we'll leave the MMR at the moment. We've been pretty averse to giving our children things that give them sore arms. But recently a meningitis vaccine has been developed, MenB, for one of the last big causes of meningitis in children. And that gives a lot of fevers and sore arms, probably 40 or 50% of children. And interestingly, it actually probably causes more admissions to hospital from the fever and irritability at that age, because you're giving it 2 months than the disease ever did. But we accept that burden, and parents actually seem to have been remarkably accepting of it, knowing that it prevents against a brain-damaging infection, albeit a rare one. So, interesting trade-off. Almost the opposite story from the 1970s is the whooping cough vaccine, pertussis, and some of you may even remember this. These is data on cases of pertussis, notifications of whooping cough, nasty illness, particularly in very young infants, thousands of them a year. In the 1950s and 60s, vaccine comes along, which is the whole bug, a whole cell, mashed up, works very well, disease falls, and then we get a resurgence of the disease here. And I don't know if anyone remembers the 1970s. Parents, public health got very anxious about convulsions and fevers with the vaccine. That had its own dynamic, and people began to stop using the vaccine, and coverage went down to about 30% for a while, and disease came back. It took about 20 years to begin to establish more confidence in the vaccine, by which time we'd moved on, and instead of using the whole vaccine, we'd taken out the proteins and we're using 3 or 4 proteins instead of the whole bug, and that seemed to give you less reactogenicity. The interesting bit of this story is that epidemiological studies didn't show any very significant, I'm hesitating with my statistical terms, didn't show convincing evidence that the vaccine was causing any significant problem with neurological disease and fever in children. Very rare cases were reported, and in the last 10 or 15 years, it's become clear that there are some very rare genetic forms of epilepsy that had only become apparent in young infants when you first have a fever. The first time most infants had a fever by 2 months or 6 weeks or 2 months of age was when they had their vaccines. And so all the vaccines did was reveal an underlying tendency which would then be developed anyway if they had a cold or something else. So there's a long play out there of 20 or 30 years of trying to restore public confidence and discovering that there's a rare genetic form of epilepsy triggered by fever. And whether you got the first fever with a cold or with your vaccine, it made no difference. You developed the encephalopathy. So it wasn't a vaccine-specific effect. Anyway, reactogenicity is a very important area and has often caused a lot of, is something that can give rise to a lot of concern. The heart of knowing whether a vaccine works are efficacy and effectiveness studies. And efficacy is the study of whether a vaccine works in a clinical trial. It's essentially in ideal conditions. And these are phase 3 studies, efficacy studies. And effectiveness is whether a vaccine works in field conditions. So we do it in a clinical trial, we decide it works. We then introduce it in a population where there are a broader group of people who get it, where conditions of storage might not be the same, the strains may vary, people don't get their vaccines on time, and then decide whether it works. But those are the two main terms, efficacy and effectiveness. Gavin made good points about design of studies. And efficacy is usually tested in a vaccine in a randomized controlled trial. You take a group of people, you randomize them, you decide who you're going to vaccinate, you randomize them so you don't have any biases in who gets what. You then follow them up closely and then look at the outcomes in terms of disease and can calculate the efficacy of the vaccine. Undertaking of a clinical trial is quite laborious, and there are many, many things you need to do to make it successful and not to end up with a false conclusion. And I've just put a list of some of them here. You need to be very clear. This is a very key statistical concept. You need to actually decide which thing you're going to study. Often studies report 20 or 30 different outcomes. Did they get sick? Did they get very sick? Did they get admitted to hospital? What was their antibody response? How red were their arms? Did praying help them? All these things. If your statistical level of significance is 5% and you're testing 100 outcomes, it's quite likely you're going to find a number of statistically significant findings. However, that's going to happen by chance. That's what you'd expect from 100 things tested at 5%. So it's very important that you define what your primary endpoint, you say before you go into this study what it is, the one thing, and it's very painful to do this sometimes, but the one thing that you're going to say is the reason for doing this trial. And in public publications, that should be the thing they request of you, because you will find other stuff and it's the secondary outcomes, and it's always more difficult to know the relevance of those. But the primary endpoint, defining a primary endpoint, is important. And I'm talking about these things so that when you're looking at the literature, if you ever do, that you look for that one thing. What was the purpose of this trial reported ahead of time? I'm not going to go through all the other aspects of clinical trials, except just the issue of blinding. It's possible to do a high-quality clinical study and still get the wrong outcome because of design flaws, and blinding would be one of these things. Our COVID vaccine participants didn't know whether they were getting the COVID vaccine or not, or the control vaccine, and neither did the staff giving it or assessing them. You might think that's bonkers. But if you think about it, if you know you've got a COVID vaccine in you, as opposed to know you've got a control, you're no longer an unbiased group of people. I've got my COVID vaccine, probably it'll work. These guys look like they know what we're doing. I'm going to go shopping, I'm going to go out, I'm not going to wear my mask. And even subtle differences in a trial of 10,000 people could bias the outcome in terms if you've exposed yourself, if the group who've got the vaccine have exposed themselves more than the group who haven't and who are worried that they're going to get COVID and they've stayed at home, you may actually find no difference between the groups when actually there is a significant difference. So blinding, so various aspects of trials which are important to be sure about the conclusions. And there are guidelines for this now. If you look at the consort guidelines, they will tell you how to report the trial, and they will ask you for reporting on all these issues above here. So the headline news from COVID vaccine trials, they gave us all these in primetime television, percentage efficacy. What percentage reduction in disease did you see in the vaccinated versus the unvaccinated population? And the Pfizer vaccine was quoted as 9%, 95%. I haven't given p-values or confidence intervals, but this was the headline news. The AstroZeneca was a disappointing 70%. The Moderna was 94%. How on earth does this mean they're different? Does this mean they all work? And I think the bottom line is, in a disease like COVID, they're very happy with all these outcomes. These were protection against symptomatic disease. And when you're looking at the comparison between studies, these were the primary endpoints. And you want to be sure that people are presenting, not just cherry-picking their data, these are primary endpoints. The things that might make a difference that are hidden by these figures are things such as the duration of the study. If one study is undertaken at a high prevalence moment for 1 or 2 months, and you get enough cases, you've got enough power to make your decision about whether the vaccine works after 2 months, that's different to a study that took a year to complete, where the cases were lower, it took a whole year because you had to wait to accrue cases. And that's different because immunity wanes after all vaccines. So if you have a study that's done over a year, it's measuring a duration of immunity in a way that a study done over 2 months isn't, and you might well expect a difference in efficacy. Studies also vary in the way they define disease. So if you have a study that says, well, you've got to be admitted to hospital, have a bad cold, have terrible symptoms, be admitted to hospital and have a positive test, you're going to get a different estimate of efficacy from a study that says, well, if you've got a snotty nose and you get a positive test, we're going to do it. So you've got to look at those sort of differences between studies. It's very sensitive. In addition, you also have the problem of regional variation. We like to do multi-centre studies across different regions because you can actually find that if you do a efficacy study in one area, you may get a different result to another. And there have been some nice examples in the past of a vaccine that worked in Finland but didn't in Alaska. And the reason being the epidemiology of disease is different, people's pre-existing immunity, their genetic background, their immune response, and many other factors. And the last thing to remember is you're not just trialling a different vaccine with these, you're also sometimes trialling a different schedule. Whether a vaccine is given at a 1 month, 2 doses at a 1 month interval, or a 2 month interval, or a 3 month interval, makes a huge difference. You actually get better immune responses the longer and longer you leave things. So in order to drill down into vaccine efficacy data, or in order to interpret these findings one against the other, you need to actually understand quite a lot about the background to the studies. The last point about clinical trials I make is reporting of trials, and 1 Corinthians 13 is a chapter of the Bible that came to mind in this. So 1 Corinthians 13 is very striking, isn't it? Not that I can remember, I didn't even have it at my wedding, but which I think is almost a sin. Is that mortal or venial? We had the Beatitudes. They thought it was a bit strange, but that's what we had. So 1 Corinthians 13, the striking thing is if I speak with the language of angels, have prophecy, have all this knowledge, if I do my vaccine study perfectly, yet I am without love, it's worth nothing. So I can be absolutely fantastic as a human being, but no love, it's worth nothing. You can do the best, even Gavin-approved study, and get a significance value of, I don't know, 5% or 4% or 3%, and it's worth nothing if it's in the context of a bunch of other studies that have been done that no one's reported. If there's 100 studies done, only 10 give positive results and 90 give negative, then if all you read is 10 published high-quality studies, that would be very convincing. I would be very convinced by that. 10 high-quality studies all give the same answer. But if that's in the background of 90 that give a negative answer, that's not the whole picture. It may be those are chance findings still, despite a well-designed study. It's a bit of an extreme example, but that has been a major problem in the literature, I think flagged up maybe 20 years ago, people not publishing all the data, and people having studies where they didn't get results they didn't publish it. And that's a big ethical issue, a bit along the lines of reproducibility. In the interest of time, I'm going to move on to safety. Effectiveness is the real-world efficacy of the vaccine, essentially. I'm going to skip over that. Correlates of protection is something we get very excited about. It would be nice not to have to do a study of 30,000 people to work out if the vaccine works. It would be nice if measuring the antibody level told you this vaccine's likely to work. And that antibody level, if it predicted protection, is called a correlate of protection. In practice, immunologists are very poor at working out what level of antibody is protected, remarkably poor given the amount of effort put into it. And it's usually impossible to license a vaccine on that basis alone. There's one exception, the first meningococcal vaccine in the UK. Meningococcal disease was licensed on the basis of an antibody response in a smaller scale study. Meningococcal disease is a nasty infection but quite rare. It was calculated you'd need to have to enrol half of the UK population to work out whether the vaccine worked. So they licensed it and went ahead and did the experiment as a national introduction. It's worked very well. I'm happy to talk about herd immunity as an ethical issue. The only things else, this was the business about transmission. Is it reasonable to immunise infants to protect their grandparents? So if I tell you the only way we're going to prevent pneumococcal meningitis in 80-year-olds is to immunise infants, is that reasonable? Is it reasonable to expect them to take all the burden of vaccine risk in order to prevent disease in their grandparents? And that is true. The infants and young people are the transmitters of pneumococcus in their communities. So pneumococcal meningitis, we vaccinated adults, ad nauseam. It doesn't work very well, but you stop transmission and it prevents pneumococcal disease. In fact, it's more cost effective to immunise infants against pneumococcal disease simply on the basis of adult disease that's presented or elderly disease. The answer is it's fine because infants get pneumococcal meningitis as well, and we only discovered that you prevented disease in the elderly because we were giving it to infants. But there's quite a lot of interesting ethical issues about immunising the transmitters and not the people who get disease. Shingles and chickenpox is another thing. If you give chickenpox vaccine to children, you eliminate chickenpox. You then get very little transmission in the community, and all of us, as we get into our older years, actually, although we don't know it, dependent on occasionally meeting a little bit of chickenpox to tickle up our immunity and to stop us getting shingles. It's predicted that if you prevent chickenpox circulating community, eventually more old people will get shingles, this sort of nasty, painful rash that leaves you with post-herpetic, post-shingles pain, essentially. So quite interesting ethical dilemmas about vaccinating transmitters to prevent disease in others. Safety, I'm going to come on to, is really the last major element of this. And this is, understanding safety is absolutely critical if you're going to vaccinate healthy people. We try in laboratories to predict safety. Very little you can do in cells away from living organisms to predict it. This is in vitro testing. Animals are used, mice and monkeys, certainly for the COVID vaccine development, but usually in numbers that are small enough not to give you great information about rarer side effects, but you can get some information about reactogenicity, although I have to say the ability to translate from animal models to humans is very limited. And then clinical studies. We undertake clinical studies whose main focus in their phase 1 and phase 2 is safety. This was the diagram I used before. Phase 1 studies, first in human, total focus is safety. Phase 2, safety plus dosing plus immune response. People queried whether the COVID vaccine had been developed unethically because it was done too rapidly, or whether there was a too rapid development and this was unsafe. This is a typical timeline. Actually, this is quite a quick timeline for the meningitis vaccine, Bexero it's called. In 2004, they went into phase 1 studies, so maybe 3 or 4 years of preclinical development. 2004, phase 1. A couple of years later, phase 2 studies. 3 or 4 years later, they're in phase 3, and only licensed in 2013, so just less than 10 years after the phase 1, and then introduced a couple of years later into the UK. So over a decade of some experience. The COVID vaccine, we first heard about COVID in December, January. Vaccines were in phase 1 by April, and we had approval of them by, what was it, late 2020, early 2021. Was that unethical to do that? Well, the answer is that there was nothing skipped out in vaccine development for the COVID vaccines. What happened is no one had anything else to do, so they were totally focused on delivering these studies. People lined up from the word go. As soon as one study was finished, they were going to analyse the data the next week, not hang around for a year procrastinating, publish the data, submit it to the safety monitoring board, and then get on with the phase 2 study. And they'd lined up the people and the timing and the funding for that. And they were already considering manufacturing right from the word go, so looking at to scale up manufacturing. So people put a huge effort to lining up the studies, getting the funding, and doing the things that usually happen sequentially. So they went through their usual process. It's possible 10 years down the line there might have been some other finding from some other field that informed things, but the studies went through the usual development process. The sort of safety data we get from clinical trials of hundreds to maybe a few thousand people is usually good for reactogenicity. Do you get sore arms? Do you get fevers? Might you get a convulsion? And we generate this sort of data where we take a symptom, chills, fatigue, fever, headache. This is by day after vaccine. This is the percentage of people that get it. And we have these little plots that quite a lot of people getting fatigue by day 2, some of it severely in red. But you generate this sort of data as to how much nuisance is this vaccine going to be. Important for public acceptability, and also important for planning your vaccine program. One thing we learned in the hospital is if you've got a vaccine where 80% of people are going to have fever the next day, don't take the whole paediatric ward staff on level 1 and give them the vaccine on the same day, because about half of them will be off the next day. So important programmatic considerations. But what about rare but serious reactions? There's a lot of focus on safety reporting in trials, and this is the sort of terminology. You report adverse events, any untoward medical occurrence during the trial. Even if it's not you don't think it's caused by the investigational product, the vaccine, you're meant to report, and there are stringent rules for doing this. Serious adverse events have all kinds of regulatory timelines around reporting them and who has to review them. And these are ones where you end up in hospital, or it's life-thresing, or permanent disability, or results in death. I mean, usually that's rare, but requires hospitalization is probably the commonest serious adverse event threshold. And then serious adverse reactions, where not only do you think that this is a serious adverse event, but you think it's related to the vaccine. And then an important bit for novel vaccines is suspected unexpected serious adverse reactions. So this is a serious adverse reaction which was no way had been considered before. If I give a vaccine, someone has a seizure with a fever and gets admitted to hospital, that's a serious adverse reaction, but it's understood that vaccines can do that. If they get some rare autoimmune condition and get admitted to hospital that's never been described before, then that's a suspected unexpected. And a SUSAR is the sort of highest level of scrutiny, the event with the highest level of scrutiny in a novel vaccine trial. Can we detect these before we license vaccines? Well, this is a table that I haven't compiled myself, but someone else has from a mathematical point of view, and says, well, look, what if there's an adverse reaction that occurs 1 in 100 vaccinees, or 1 in 300, or 1 in 1,000, or what if only 1 in 10,000 vaccinees, but it's a serious thing? In my trial, if I had 300, 400, 600 participants, how many cases of this rare condition would I pick up? Well, even if it's a 1 in 100, so quite a common rare condition, to pick up more than 2 cases, I'd need sort of 600 participants in a trial. If it's a rare condition, 1 in 10,000 participants, in order to get 3 cases, I'd need to do a study with 65,000 people in. So what it tells you is, on the whole, it's not feasible to expect rare, even though there are important serious side effects, to be picked up in the clinical development part of vaccine studies. This became important in the COVID vaccines. The vaccine study was halted for a while, the AstroZeneca one, because someone developed a transverse myelitis, a rare, serious inflammatory condition of the spinal cord in the days after vaccination. You get a SUSAR, suspected, unexpected, serious adverse reaction. Studies stopped, data is reviewed by the Data Monitoring Committee, and if they're happy that it can't, with the balance of risk and benefit for the study, then it's either the study's recommenced. If they're not, maybe they've had 3 other episodes before in the study, then it's halted. But this is a part and parcel of clinical studies. So, rare adverse events. Maurice Hillman was one of the vaccine pioneers, I think, of the 40s and 50s, judging by the photograph. this was his comment: "I never breathe a sigh of relief until the first 3 million doses are out there. It's been well recognised from a long time ago that there are very rare but significant effects that you will only find after you introduce the vaccines." A lot of effort was put into proactive surveillance once the COVID vaccines were in use through the yellow card system by the Medicines and Health Regulatory Agency. And in America, they have a passive vaccine event reporting system to try and pick these events up. This is some of the articles after in the phase 4 studies. So post-licensure, these vaccines were in use across the world very quickly in millions of doses, so provided a very rapid opportunity to find about rare events. So I don't know if any remember the first 2 or 3 days of the use of vaccines, people reported a little series of severe adverse events, anaphylaxis to I think it was the COVID or AstroZeneca or Pfizer vaccine. It turned out that was just coincidence. It didn't carry on happening at any particular high rate. But of more importance were a small number of males, particularly after the second dose of the Pfizer vaccine, got a myocarditis, an inflammation of the heart. And even more significantly, and these were almost universally non-fatal, more significantly after the AstroZeneca vaccine, they reported an unusual clotting disorder which involved cerebral thrombosis. How to distinguish, were these genuine? Are they like signal from noise? Were this like the transverse myelitis, a one-off event, it's happened by chance, or were these significant? And there's quite a lot of guidance now on how to assess causality. Are these consistent findings across different studies in multiple different settings? Is this a strong association that it's a condition rarely reported naturally and therefore that it's strongly associated with vaccination? Is there a temporal relationship? If something's 10 years after the vaccine, it might be related, but it's going to be very hard to show. If you're getting cases of myocarditis immediately after the vaccine in the first week, it's more likely. And is it biologically plausible? If 100 people in a study of 10,000 get run over by a bus after the vaccination, there's not really a high biological plausibility that your vaccine has caused that. If you've got a rare inflammatory condition, it's slightly more likely. In the end, the myocarditis risk was thought to be in young adults, something like 22 to 31 cases per million doses. And those were non-fatal. For the AstroZeneca vaccine, the thrombosis risk was thought to be 15 cases per million first doses. So, and with the myocarditis, it was after the second. So real significant risks of serious conditions should we use the vaccine. And I guess this is where people begin to study the balance of risk and benefits. And this is some graphics I've got from the Winton Centre for Risk and Evidence Communication, essentially trying to weigh up what are the potential harms. This is for every 100,000 people, how many individuals in a period of 4 months in a setting of relatively low exposure to the virus get the complication of the vaccine versus get disease requiring admission to hospital. And you begin to balance by age group. Actually, it's pretty finely balanced all the way down here. If this is a potentially fatal clotting disorder, and even if you've got 1 per 100,000 here and 3 per 100,000 admitted to ITU, you might prefer to be admitted to ITU with COVID than to have the vaccine. In a setting of high exposure where there's a lot of disease circulating, as there was in at times in our population, then even as the risk of a potentially fatal thrombotic condition is outweighed by several tens of cases admitted to ITU with mortality. So rare events do occur. They're hard to pick up in clinical trials. You need accurate and you need methods of post-vaccine licensure surveillance, and you need people who will weigh up the risks and benefits. I'm going to scoot to the end because I suspect we're at coffee time. Lots of interesting stories about safety, but we'll skip over that. I'm not going to talk about scheduling. I'll just finish, except for the last slide, about information and disinformation. If there's any ethical issue of our time, it's the ability to provide accurate, reliable information, both from a scientific point of view to help make decisions about whether to use vaccines or not, but also to help inform parents. And one of the jobs I do is doing a clinic in immunology, infectious disease. We see a lot of people who are confused about what they're reading. And it's, you saw Gavin's litany of BBC reports and journal articles. It's actually, even for someone with a professional interest, if you take a particular question, does this cause this, does this vaccine cause this condition, it's a good bit of work to search through the literature, dig out the analyses, weigh them up, think about it, to come to a conclusion, a firm conclusion about it. For parents, it's an utter nightmare. I mean, they're presented with a lot of bad things, and they're having to take the decision to commission an act against, that might harm their child. There's a lot of research going into how best to counter this. And people worry that the World Wide Web, and this is meant to be some study looking at websites, looking at which are connected to which, pro-vaccine, anti-vaccine, and trying to work out how to break up networks of anti-vaccine sort of sentiment. I'm not sure whether it's worse to have social media than it was previously. When you look back at the furore around some of the smallpox mandatory vaccine, adverse public comment and disinformation, it was there right at the start. People were anxious about things, discussing them, disseminating poor information. It may be with social media we just get our thing comes along and it's over us in a much more quicker burst, because everyone hears about it, a lot of discussion, upset, but then actually things are put to one side. So I don't know if social media is definitely worse. I'd like to believe it is. But it's certainly a major issue for parents, and I think as much as getting the truth about the risks for them is usually finding someone they believe and trust. And that person that they trust has to have accurate information, be it you or me or the midwife. I'm not going to talk about long-term surveillance. I will finish there. Those are the things that vaccinologists talk about. Quite a lot of them have issues around ethical issues. And if you have to pick out two ethical issues about vaccines that I think are probably the most important ones of our time, I don't think they're HEC 293 cells. I think it's equity, choosing to engage in programs of research for diseases that affect people who maybe don't have the resources to do it themselves and cover strains that are important for them. And truth, which is the scientific truth Gavin has been talking about, and the truth for parents, and whether actually trust in the end is more important for the parents than truth, but the people that they're trusting still need truth. I think those are probably two of the biggest ethical areas around vaccines from my perspective. Bit of a scoot through things. I'm sorry it's quite quick, but there we are.